Isn't it amazing when things glow in the dark? Wow! You turn off the lights and suddenly there it is. A spooky Halloween skeleton starts to shine. Or maybe those cool stars on your bedroom ceiling begin to twinkle. It's like magic, right? But guess what? It's not magic at all. It's science. And science is happening all around us, all the time, even in the dark. We are going to explore this glowing phenomenon together. Prepare to be illuminated, scientifically speaking, of course. This is some seriously cool stuff we're about to dive into, so get ready. Think about it, you've seen it. Those awesome stickers, the hands on a watch, or even some kinds of paint. They all have this incredible ability. They can light up all by themselves after the main lights go out. How do they do that? Do they have tiny batteries inside? Nope, not usually. It's something much more fundamental, something to do with the very nature of light and matter. It's a fantastic display of physics in action. We're going to break it down step by step so you can understand the science behind the shine. This glowing power has fascinated people for a very, very long time. Let's get glowing. First things first, let's talk about light. What is light anyway? Well, light is a form of energy. Think of it like this. The sun sends out light, and that light carries energy to Earth. This energy warms our planet and helps plants grow. Light travels in tiny packets, almost like tiny bullets or waves called photons. These photons are zipping around all the time, bouncing off things and going into our eyes so we can see. It's pretty incredible when you stop and think about it. Light is essential for almost everything on our planet. Now, the light we see, visible light, is just one part of a much bigger picture. There's a whole spectrum of light, much of which our eyes can't detect. There are radio waves, microwaves, infrared light, which we feel as heat, and ultraviolet light, the kind that can give you a sunburn. Then there's X-rays and gamma rays too. All these are forms of electromagnetic radiation, just with different amounts of energy and different wavelengths. For our glow-in-the-dark stuff, we're mostly interested in visible light and sometimes ultraviolet or UV light. When light hits an object, a few things can happen. It can bounce off, which is called reflection. That's why you can see a shiny red apple. It reflects red light. Light can also pass through an object, which is called transmission. Okay, so we know light is energy, and we know that some materials can absorb this light energy. But how does that actually happen? It all goes down to the atomic level. Atoms are the tiny building blocks of everything. Inside atoms there are even tinier particles called electrons. These electrons usually hang out in specific energy levels, kind of like rungs on a ladder. They are comfortable in their usual spots, their ground state. It's their home base, where they like to be. When photons of light, especially from bright light or UV light, hit these special glow-in-the-dark materials, they can give their energy to these electrons. If a photon has just the right amount of energy, an electron can absorb it. This gives the electron a big energy boost. It's like the electron just drank a super-powered energy drink. With this new energy, the electron gets excited. It can't stay on its usual low-energy rung anymore. So it jumps up to a higher energy level, a higher rung on the ladder. This is light absorption in action. The material has now successfully absorbed the light energy and stored it, at least temporarily, in these excited electrons. So our glow-in-the-dark material has absorbed light. Its electrons are all excited and hanging out on higher energy levels. They're like tiny coiled springs full of potential energy. But they can't stay up there forever. Everything in nature likes to be in a stable, low-energy state. Those excited electrons want to return to their original, comfortable ground state, their home base on the lower rungs of the energy ladder. It's just a matter of time before they decide to make the journey back down. When these electrons finally do fall back down from their excited state to their ground state, they have to release that extra energy they absorbed earlier. Where does that energy go? Well, in glow-in-the-dark materials, a good portion of this released energy is given off as light. Section 5, Phosphorescence, the science of the slow, magical glow. Now let's talk about a very important science word, phosphorescence. This is the scientific term for the type of glow we see in most glow-in-the-dark toys and stickers. Phosphorescence is a specific kind of photoluminescence, which just means light produced by absorbing light. What makes phosphorescence special is that the material doesn't re-emit the light immediately. Instead, it stores the absorbed energy for a significant time and then releases it slowly. That's the key, the slow, delayed release of light. The magic behind phosphorescence lies in the material's atomic structure. These materials, often called phosphors, contain certain chemicals usually involving zinc sulfide or strontium aluminate, mixed with an activator like copper or europium. These activators create special traps for the excited electrons. When an electron jumps to a higher energy level, it can get caught in one of these traps. It's like the electron wants to fall back down immediately, but the trap holds onto it for a while. This is a very clever trick of nature and chemistry working together. Because the electrons are trapped, they can't just drop back to their ground state right away. They need a little bit of help, often just the natural vibrations of atoms at room temperature to escape these traps. Section 6. Quick glows versus slow glows. Meet chemiluminescence. While phosphorescence is super cool for making things glow for a long time after charging them with light, there's another type of glow out there called chemiluminescence. This is a bit different because it doesn't need to absorb light energy first to start glowing. Instead, the light in chemiluminescence is produced by a chemical reaction. Chemi means chemical, and luminescence means giving off light. So it's light from chemicals mixing together. It's a one-shot deal usually. You've probably seen chemiluminescence in action with glow sticks. Those fun, colorful plastic tubes that you snap and shake to make them light up. When you snap a glow stick, you're breaking a small glass vial inside. This vial contains one chemical, and it mixes with another chemical that's already in the plastic tube. When these chemicals mix, they react with each other. This chemical reaction releases energy, and some of that energy is given off as light. No batteries, no prior light charging needed, just chemistry. Section 7. Glow-in-the-dark goodies, fun stuff all around us. Now that we're experts on how things glow, let's look around. Glow-in-the-dark stuff is everywhere, and it's not just for fun, though the fun stuff is pretty great. The most common things you might think of are toys. Those plastic stars and planets for your ceiling. Classic phosphorescence. Spooky Halloween decorations like skeletons or spiders that light up after dark. Yep, that's our friend phosphorescence again, working its slow glowing magic to add an extra layer of eerie excitement to the night. But it's not just toys. Think about safety. Many emergency exit signs use phosphorescent materials. If the power goes out in a building, these signs will still glow, helping people find their way to safety. That's incredibly important. Some paints and tapes are also made with phosphorescent pigments. Section 8. Beyond the bedroom stars, the bright future of glow. The science of things that glow is already pretty awesome, but scientists are always exploring new possibilities. The future of glow-in-the-dark technology, especially advanced phosphorescent materials, is incredibly bright. Researchers are working on developing new phosphors that are even more efficient. This means they could absorb light more quickly, store more energy, glow brighter, and last much, much longer. Imagine a glow that could last for days instead of just hours. That would open up so many new applications. One exciting area is in sustainable lighting. Think about pathways or even roads that could absorb sunlight during the day and then glow gently at night. This could reduce the need for electric streetlights in some areas, saving energy and reducing light pollution. Scientists are experimenting with incorporating super strong phosphorescent particles into concrete or asphalt. This could make our cities safer and more energy efficient. Section 9. Conclusion. Keep shining and exploring science. So there you have it. The amazing science behind things that glow in the dark. It's not magic, it's physics and chemistry doing their wonderful dance. We've learned that light is energy, and special materials can absorb this energy. Their electrons get excited and jump to higher energy levels. Then, in phosphorescent materials, these electrons get trapped for a while. Slowly, they fall back to their original spots, releasing their stored energy as that beautiful, gentle glow we love so much. It's a fantastic journey of energy transformation. We also discovered that there are different kinds of glows. Phosphorescence gives us that long-lasting shine in toys and safety signs, rechargeable with light. Then there's chemiluminescence, where a chemical reaction creates light like in glow sticks or fireflies, a one-time show but still super bright and cool. Understanding these differences helps us appreciate the variety of ways light can be produced in our universe.